we are now predicting dependent variables. It builds on correlation. We're basically using insights and methods from correlation to essentially now use this to predict dependent variables. So simple linear regression statistical tool predicts a dependent variable based on the score of one independent variable. And I just want to quickly go back now to the spreadsheet we worked on in last class. So we did last class, we did in the last class, we did our exam grades as a function of absences from class. So we saw an inverse correlation. That means the more absences, the less the exam grade. So the worse the exam grade. So what we see here is basically a regression function, which basically was here an inverse relationship indicated by a negative slope in your function of your line. So this is a regular line function. So again, just as a recap, the y is predicted as a function of slope multiplied by the x, so the individual x entry, plus the intercept that is basically that point where this function crosses the y-axis and x equals 0. So this is how you define a line in a Cartesian system. You have here with the R square, you have a depiction of the numerical quantification of the prediction accuracy of your regression function. So just for all further conversation, try to keep in mind what we're looking at here. We have a scatter plot and we have the line of best fit, and the regression model essentially is characterized by a line in a simple univariate analysis. And this is what we will be referring to in the following. So we have now to discuss an association that derives arithmetically. You remember from the correlation coefficient, we basically looked at a numerator and a denominator, which allows us to calculate the correlation coefficient. This coefficient basically has the numerator, which is the sum of the products between the deviations of x multiplied by the deviations of y, which determines the direction of this association. And there's a reflection of that angle it has deviating from a 45 degrees perfect correlation. This also gives you the direction of this association. So it's going to be either negative or it's going to be positive. Then you have in the denominator, you have the variability of your data. So you have it depicted in the denominator as square root of the product of sum of squares on the x multiplied by the sum of squares of the y. This gives you the information independent of a sum, because the sum of squares is always positive. You're squaring it and you employ the square root. Basically gives you a positive estimate of this variability of both jointly, of both dependent and independent variable jointly. So now we're going a step further. When you have a y variable, your dependent variable, and you have an x variable, you can just in the same fashion as we've done it in the beginning of the semester, we're standardizing our individual scores on a normal distribution. You can do this again with your independent variable x. And if you standardize your independent variable x and you multiply it any independent variable of interest. So if you think about the example with the absences in class, you can basically take any particular absence and you can standardize it in the light of that mean that you have calculated from your x entries. So you have in the same fashion, you calculate your standardized x, and multiplying the standardized x with the correlation coefficient, incorporating the direction as well as the variability, gives you now your corresponding predicted y standardized to the mean of y. So you can estimate for each x in relationship to its mean the same corresponding standardized coefficient for your y. So this equation here, set y hat equals r xy multiplied by your standardized x, gives you an ability to actually predict your y. And this y hat, whenever you see a y with a little hat on top, that actually indicates it's a predicted value. And this is important to keep in mind also then further when you're being exposed to statistics again. Whenever you have a hat on top, you're looking at a predicted value from a model, most likely a regression model. Good. This being said, if you're operating now with a correlation coefficient of 0.58, which is, as we remember, it's a large coefficient, so it's a large correlation. You have basically now a standardized x that is -1, -2, +1, +2, and 0. At 0, your predicted set score is 0. If you look at set x, you have -0.58. If you look at set +1, you have 0.58. So basically it goes now in increments of 0.58. It comes and basically in the same fashion, it goes stepwise with the standard deviation. Remember the definition of a set score. This is the expression of each individual score from the mean, expressed as the number of standard deviation that's away from the mean, right? So you can now relate set x and set y with your correlation coefficient. So basically, it captures the distance between one standard deviation to the mean expressed as a correlation coefficient. And this is this relationship. And this is also essentially the basis for the so-called regression to the mean. The regression to the mean says that arithmetically, every single regression function that you will see will always go through the mean of both x and y. That means this is going to be the center point of your prediction. And that's important because you may be using this to really predict values that are more extreme, that are far away from the mean. And this is usually where your regression prediction will get more inaccurate. And the most accurate is only where the mean is, where the bulk of the normal distribution is. This will be discussed in the following, then on the example of stock market values. We can actually go there quickly. So what you see, for example, here, this is a regression to the mean example, where basically you have two different time periods, and you basically see a prediction where basically the extremes tend to then gravitate back to the smaller values in the second period. So that means extreme outliers will always tend in a future analysis gravitate back to its mean, also in time series analyses. But that's not the main observation, and that's not the main definition of the regression to the mean. What's really important that whenever you look at a scatter plot, you will always know that the center of this prediction and the point where it's most accurate is where the mean is. Okay, any questions on any of this so far? If not, then we can actually now get started with our example. And this is bringing this all kind of in context. Okay, so keep in mind, correlation coefficient, we have calculated last time. We have a regression equation, which is nothing else but a line function. And we want to find out what this line function looks like. And we want to basically use this to predict y using x. And knowing this association between set x and y, or set y, by the correlation coefficient, we can actually utilize now data that we have, not this one, let's take this one. data that we have on canvas, which basically shows an association that's quite interesting because it's also being used clinically. So when you have a stressful life event, you may have a higher incidence of depression later on in your life. So this basically means to quantify a back depression inventory score, which is a marker of depression. And you have the original publication from the 1960 on Canvas, actually, if you want to read up on it, as a function of stressful life events, of the number of stressful life events an individual has experienced. We have data of 10 participants or 10 individuals and their respective corresponding depression score. So now we need to find out a couple of things. The first thing we want to know, is there actually a correlation between these two variables? So the way you would approach this first is, and you remember this from last class, I hope, is to first build a regression plot or a scatter plot. So you do that quite easily. You're selecting X and Y, and you're just going, as always, on scatter plot. You get your scatter plot, and you see already there may be some associations. So I'm zooming in a bit. There may be some association that probably points to a positive association. That means that your dependent variable increases with an increase of your independent variable. That means depression increases with the number of stressful life events, which reasonably makes sense, right? Not being a psychologist, but I could see kind of this association to be true. Good. So now let's label this quickly, just for the sake of completeness. So we have here stressful life events. And we have here depression score. Good. So one way we always can look at this is by just fitting a function through that. If we add a trend line to a scatter plot, we see an increasing association. So let's see how well this actually can be utilized to predict our association. First thing we first want to characterize our population and the characteristics of our sample. So we're building first an average. That will basically get us the average life events, which is 1.9. Then we get an average of our depression score, which is here 15.7. So that's the average. Then also, since we're dealing with Z scores, we will need a standard deviation. It's always nice to look at data in terms of the variability. We will also quantify a standard deviation, which is here 1.6 and 9.35. Good. Correlation coefficient, we said, first product of the deviations summed up, divided by the sum of squares. So that essentially gets us to, first we need to quantify our product deviations, product deviations. So this is essentially now this individual X, let's say parentheses, this individual X, 1 minus 1.9. We just need to lock this in that it doesn't shift. Multiplied by C minus this. So that gives us the deviations. So this essentially is now our product of the deviations. We can put this all the way down. Gives us the product. Now we just need to sum this up. Gives us the sum of products. So that's our numerator. Next, we just need the sum of squares of X and sum of squares of Y. This is, as we know, we're getting this by our X minus our mean x, squaring this up. Now we're doing the same with y minus my, which is c. Now just summing this up. Then we just need to sum these squared results. And then essentially we can calculate our R. And our R is basically this divided by the square root of this multiplied by this, right? So we know this to be the way how to calculate your correlation coefficient, gives us 0.58, just like in our example with the standardized coefficients. Okay, but now we're going a step further. So now you want to calculate, we have done this last class. So now we want to actually predict our standardized y hat. First thing we need to do, when we look at this scatter plot, we want to know two things to develop our regression function. We need a slope, where the slope essentially quantifies how much is this function, this dependent variable, increasing from 1 to 2, or from 2 to 3, or from 3 to 4. So we want to know how much is that increase. Secondly, so that's the slope. Secondly, we need an intercept, and this is where this line crosses the y-axis, where x equals 0. These are the only two things we need to know. And I'd say we will start easy. So we have an x, which is stressful life events. Which is now, let's start with 3. Let's go down to 2. Let's take 1, and then let's take 0. That's the last one. Good. So far, so good. Now we need to standardize this. So the set x, let's do that from set x. Set x is now this minus our average x, which is stressful life events, divided by our standard deviation. And the standard deviation we have calculated, so we need to standardize it. So now we have for set x, we have 0.66. We have for, for 2 stressful life event, we have 0.06. For 1, because it's less than the mean x, we have minus 0.54. And for 0, we have minus 114. So now we know that if we want to get to set y hat, we just have to multiply this by the correlation coefficient. Gets us essentially 0.38 for 3 stressful life events, 0.03 for 2, minus 0.31 for 1, and minus 6.66 for 0 stressful life events. So now remember, standardization is x minus mx divided by standard deviation. If you want to come the other way around, you need to calculate the standardized set multiplied by your standard deviation plus the mean. That gives you the actual raw score. So this actual raw score now is y hat. And this is basically calculated by set y hat multiplied by the standard deviation of y plus the mean of y. Right? So this gives you an actual estimate of your y. Gives you for 3 stressful life event 19, 16 for 2, 13 or 12.8 for 1, and 9.5 for 2 for 0. Okay, simple, right? So that would be 19, 16, 12, and 9.5. Makes sense? Reasonable? And now let's go back to the definition of a slope. So we need a slope and an intercept of our function. We want a function that is essentially in the following format. It's y equals slope multiplied by any individual x plus an intercept. The slope is the difference from one x to the next x, a numerical increase of 1 in the x, in the independent variable, gives you basically the slope. So if we want to know that slope, if we take the difference between 2 and 3, that would be the increase, right? With 1 unit of the independent variable. So if we're calculating the difference between y hat 3 minus y hat 2, that would essentially be our slope, which is simple, right? Particularly in the light that this will be, oops, this would be the same for the next one, would be the same for this one. So all of these increases are always the same slope. They're always 3.24. So that's our slope. Another $1 million question is, what's the intercept? And that brings us back to the definition of the intercept. So again, the intercept is where that function crosses the y-axis and x equals 0. So exactly this point here at around 10, and I'm not exactly 10, would be our intercept. And again, when you look at this definition, you have this value already here, because x equals 0 corresponds with an arithmetically derived y of 9.54. So that's our intercept. So the intercept is this. So that gives us now a regression function of y, dependent variable, equals 3.24 multiplied by x plus 9.542. Makes sense, right? It's not too complicated. But all the steps in between are quite important to keep in mind, particularly the transition from x to zx and from zx to zy hat. And please keep in mind that this is a predicted y. This is a predicted dependent variable that you're deriving here. And once you have this predicted variable, you can then easily employ this function to your population. And this is actually what we're going to do next, with one particular reason. Because not only do you want to fit a line through, so now you basically fit that line through. You calculated, not this one. You calculated what this line looks like. So you developed the function for this line. And these predictions, as you can imagine, these predictions do have an inherent error. So it's not the accuracy of that prediction will likely, since you only use one variable, quite debatable, right? So you will have an estimate and you will have a difference from an actual value, from an actual observation to your predicted value. And this essentially gives you an error to your prediction. And this error is called a residual error. So each individual point and its distance to the predicted line or to the predicted value is called a residual error. And why is that important? Because that standard error for the overall model will basically allow for you to quantify the predictive accuracy of your model. And that predictive accuracy actually means which prediction would you believe more? What prediction actually makes more sense? The prediction here or the prediction here? And I think the answer is quite obvious because it's just much more accurate on the left side, right? And so now you need a tool that allows you to quantify how accurate is my model. And this tool is essentially the so-called proportionate reduction in error, or also called coefficient of determination. So it basically means how accurate is now the prediction of my value when I use this regression function actually, rather than just use the mean of y. So I could also say it's like I have now my mean y, I have my mean depression score for my overall population that has a certain kind of predictive quality, and I just take all these 10 individuals and I predict each individual that comes to my practice now as next was just taking the mean of my population. That will not be very accurate. So now additional accuracy is being provided to you by building a regression function, because now you have a function that actually gives you a tool to quantify this with more certainty and more accuracy. And the coefficient of determination, or the proportionate reduction in error, allows you to quantify how much information do I gain from building out this regression function. How much of this overall variability that I see in my scatter and my data is now being explained by my regression function. And this is quantified with this simple calculation. It's basically SS total, it's the sum of square total. That's the mean minus the individual score squared. These are our squared deviations, and you get to that sum of squares, minus the residual error of the overall model. And that basically requires for us now to understand how much error do we have with the model. If we utilize the model to predict our individual depression scores, how accurately does that predict these values that we have observed? And this essentially is simply done. So we have the sum of squares already here. This 788, that's our sum of squares. That's our actual variability that we're observing in our dependent variable. So now next we want to utilize now a predicted y, our y hat, and y hat is essentially calculated with the regression function. So you have now our slope, which is 3.24, we're just locking this in, multiplied by the individual number of stressful life events for each individual, which is one for the first individual, multiplied by this, plus, and this is where the second part of the regression function comes in, plus the intercept. I'm just using the actual intercept because it gives us all the decimals, makes it a little bit more accurate. So now adding this up, the predicted y hat for individual number 1 would have been 12.8. When looking now at the actual value, you see already that individual number 1 actually had a depression score of 24. What's the logical conclusion from that? The model is actually not that great, but still it may be better than just using the mean. So if we complete this series now for each individual, there's now 6.5 for individual 2, here the score of 20, 6.5, score of 18. Well, it's not getting better. But this is the problem, right? This is the problem you actually have with regression model, particularly when it only contains one variable, because it will regress to the means, and the extreme outliers it will basically ignore. It only will get in the overall error. If you look in the respective magnitude of that value, the further you go away from your mean, the more inaccurate it becomes. So there will be a decrease of the precision, so to say. And essentially you will get wider confidence intervals with your prediction. And it's only going to be somewhat accurate somewhere around the mean. And the mean is here at 15.7. So when you look here at individual number 9, You have here y hat, the predicted y hat of 16, and the actual observed value is 15. So it's a little bit more accurate around this area. But more about this later. Okay, so y hat, this is our predicted y based on our regression function. So now we want to calculate what's that error, what's this residual error. And this can be done by y hat minus the actual observation. So you can always do it the other way around. You can calculate this minus y hat. It's actually more intuitive in a second look. So we have now here an overestimate, an underestimate of 11. It's actually the other way around. This better, like the other way around. More. So we have here an underestimate of 11. We have with individual number 2, we have an underestimate of 13, underestimate of 11, and so on and so on. Here we have an overestimate. So basically errors more to the lower end. So now as the next step, so we want to quantify sum of squares. And this is why I told you in the beginning, sum of squares, please memorize that, because it's gonna come back again, particularly when it comes to ANOVA and regression. And we are again quantifying a sum of squares as our metric of variability. And here again, we have residuals. Now we need the residual squared, which is essentially residual squared. We're quantifying this for each individual, and then we're summing this up. Gets us a bit, oops, that's something off. Yeah. There was a little mistake in there. So we're calculating this difference here. We get to a squared residual. And now here to the rest error. And this is the residual error after utilizing our model. So this is the leftover error after utilizing the model. So if you want to know now how much did the model contribute to my prediction and to my accuracy, you can do this by calculating, and this is called, so this is sum of squares total. This is sum of squares residuals. So this is the residual error. And now we have a sum of squares for our model. So that's the sum of squares regression. So that's the variability, or that's the contribution to the prediction of the model. This basically gets us now 788 minus our sum of squares residual, gets us to 261.55. So that is what our model contributes to the accuracy of the prediction, to that scatter, what it explains from that scatter. So as outlined here by Nolan and Heinzen, R squared is now calculated as sum of squared total minus sum of squared error, which we have calculated, divided by our sum of squared total. So we're getting a proportion of our explained variability divided by our total variability. So R squared equals 261 divided by the total variability of 788. That gives us an R squared of 0.33. So again, this is the proportionate reduction of error of the overall scatter plot. This is what you're explaining now by employing this bivariate model, this bivariate regression model. Any questions so far? No? If you want to go an easier pathway, obviously there are several easier pathways. If you have Excel at your disposition, you can display the equation on the chart. Once you click on the trend line, that gives you exactly this equation. Alternatively, you can, in addition, you can also click on display R squared, and this is exactly the same R squared we calculated. Of note, and I'm making this note with caution, because it's only applicable in univariate analysis, meaning there are only two variables involved. There's one dependent, one independent variable. In that case, and in that case only, you can estimate the R squared also by squaring your correlation coefficient. That's where it has its name from. That's why it's called R squared. But I raised caution about this because once you have more than one variable in your model, which we will discuss next time, whether it actually will be the case in multivariable regression, you essentially cannot do that. So there's a different arithmetic at work than it is here. Okay, so far so good. So again, so we have 10 individuals. We have for each individual a corresponding number of stressful life events. We have corresponding depression scores. We've calculated the averages and the standard deviations, utilized these insights to basically calculate our standardized X. We have utilized this standardized X to estimate using the correlation coefficient, a standardized Y hat, a standardized predicted depression score. We have then utilized the mean of our actual Y and the variability of our Y to basically come back to our actual predicted Y. So that's essentially the angles of the dependent variable on our regression function for the corresponding X values. We have utilized then, and this is what's becoming more important, also thought-wise, because you can continue this prediction ad infinitum, because that line is not going to end before infinity, right? In both directions. So in case there were minus stressful life events, you could predict it in that direction as well, which you may be doing for some use case examples of regression. But you can say, okay, so I have now this individual in front of me has like 15 stressful life events. Like, what do I think based on my function, what his depression score will be? So you can continue this in any direction. And you will actually find an example like that on the homework. Okay. What else? Yeah. Based on that, we developed the regression function. The regression function, this is important. This is always to be kept in mind. That the slope multiplied by X will give you, and adding the intercept will basically get you to this function that you can utilize to predict values. The slope again is the increase in the dependent variable with 1 unit increase on the of the independent variable, and the intercept is the numerical value of the dependent variable where the independent variable equals 0, and that will never change. That's always the same formula. Based on this, we have then calculated for each of our 10 individuals our predicted Y. Have then calculated the difference of our predicted Y from the actual observed Y, have squared that up, and have derived our residual error after employment of our regression function. So logically, the difference between our total sum of squares calculated as the difference between our individual scores and the mean, and the sum of squares residuals, which is the difference between our predicted and observed Y, gets us to our sum of squares of the regression, which is basically the explanatory power of this function in a way. And the proportion of this explanatory capabilities of the model to the overall variability gets us to our proportionate reduction of error, coefficient of determination, or R squared. Simple so far, right? It's not terrible, but it is one of the logical and one of the most brilliant statistical approaches that you could think of, because you can, based on that, the pool of things you can do with a regression model is limitless. And this is we're only not even scraping the surface of regression. So essentially, when you further your statistical education moving forwards and you do some applied biostats step 1 or something like that, you will basically focus an entire semester on regression analysis. So there's so much more to regression than just that. And you can in regression analysis, regression analysis uses F-statistic, just like the ANOVA, because you can conduct an ANOVA using regression model. You can literally, you can also, you can do t-test. A t-test in a regression model basically substitutes the t-test. So it's a very elegant way and approach to various questions that you have. And we're not going to dig deep into regression, but just rest assured there's a lot of material around regression, and it's a wonderful method. Good. Okay. So this was pretty much all of the calculations at this point. So we have talked about a regression line. We've talked about slopes and intercept. Again. We have talked about the line of best fit. Also the method, that's maybe the last one. Yeah. Arithmetically, keep in mind, maybe this is not too much information. It's actually, it's a nice arithmetic exercise that when you actually would go and using the spreadsheet. So we have here the sum of the squared residuals, right? What would you think will be the sum of the residuals if you would just sum those up and you wouldn't square them first? And it's a funny arithmetic exercise, because when you go through each step of the calculation and you look at it, because it's quite obvious, but it's such a complicated stepwise approach that it's at this point not even that obvious anymore that the sum of these residuals actually must be 0, because it gravitates over around the regression, around the predicted regression. Also, what's also interesting is that the average, and also this is not very obvious when you don't think about it specifically, because the average of the squared residuals, no, the average, no, not the squared residuals. Square them back. Yeah. Okay, thought process. Okay, so but the sum of these residuals is 0. I was thinking a little bit around the corner here. Okay, so the sum of these residuals actually is 0, and basically what you know about yeah. Okay, there was one observation that I cannot share in univariate analysis. Doesn't matter. Okay, good. Okay, so the sum of this residual is 0, just to keep in mind, because you predicted something based on these. You predicted something based on a prediction, right? And this prediction basically was built exactly in that same way that you're closing backwards. That's why the sum has to be 0. What's also important in this context, these residuals will also show a normal distribution in this prediction. So it's basically it is an unknown standard deviation that will be related to the sum of squares residual, obviously. So if you divide this by the degrees of freedom of your actual data set, you will again get a standard deviation, and you will basically have this distributing around the mean of 0, or it's a mean of 0, around the mean of 0, that essentially will form a normal distribution. So the residuals per se are normally distributed, which is actually one of the assumptions of a regression analysis and the correlation analysis, if you remember. Becomes important then later on. What else is important about this? Yeah, the residuals actually will also then in the following. So we talked about this. The residuals actually are also be visualized in many situations. So you basically have two forms of residuals. One is the residual from the actual mean. So this is our 15.7 mean of the dependent variable, and these are just the residuals. So this is the total error. And that's a nice way to actually depict that, that Nolan and Heinzen showed here. So this is our total error. That's the sum of square total. And this is our sum of squares residual. So that's the leftover error by this regression function. And each individual difference is one residual. Okay, well, we talked about this. And then lastly, you have the regression to the mean. So this occurs when extreme scores tend to become less extreme over time. That's the example with the stock market we talked about. And then lastly, to predict something with more accuracy, you will also factor in additional variables. And this is what you do with so-called multiple regression or multivariable regression. And this is where things become a little bit more complicated, but they also become much more exciting. Because a lot of the work I do is essentially to find out which variables to include in such models. It's called adjustment. It's called adjustment of regression models, or whatever fancy model you would be using. But they all kind of follow the principles of regression. So if you include additional variables, you explain more of this variability. And thereby you increase your predictive accuracy of your model. The problem is you need to know what you're including and what you mean to include and why. And this is, if you remember in correlation, I talked about directed acyclic graphs, so-called DAGs. This is basically what you would be mapping out to make sure that you don't have things that are correlated, quote unquote, collinear, and that they actually don't affect the accuracy in a negative way, which unfortunately happens quite frequently. So here with the example, and we'll talk about this more in detail on Wednesday. Here in this example, you have now a number of stressful life events. You again have the dependent variable back depression score. And here you factor in the sleep disturbance score, because people that don't sleep well also are more likely to be depressed. That's well known. So including this is something that we will not do arithmetically, because that's quite some heavy lifting. But we will do this in R. And this is in R shown in a different format than here. This is a printout of a software called SPSS, which personally I have used it for quite a bit. I'm not a big fan, but it is quite user-friendly. So some of you who may do some additional analysis or additional statistical courses will be exposed to SPSS. It's very user-friendly. It's basically drag and drop and click and play. So you can take the variables, just drop it in some field, and it's going to be simpler than R. But it's also not as great as R. Good. What you have here is basically the same output. All outputs, all statistical softwares will show you data in the same way and fashion. So what's important for you to keep in mind is you have here different columns. So you have here the model, including different variables that were included in the analysis. You have here the so-called unstandardized coefficients. And the unstandardized coefficients are exactly what the name implies. They're unstandardized, so they're not standardized like these, which are basically the SAT scores. No, these are basically the unstandardized coefficients that literally you can use to predict an individual dependent variable, an individual entry of a dependent variable. So if you have an individual that comes into your office and says, okay, so I haven't been sleeping well and my sleep disturbance score is XYZ, and I had 3 stressful life events throughout my life, you can use this equation basically in the same format. You have here the intercept. You have this is slope 1 and this is slope 2. And you're just adding this intercept with life events multiplied by 3. So this multiplied by 3 plus sleep score multiplied by 2.0989. And that's how you can estimate the individual patient's depression score. Of course, unfortunately, again, with a certain kind of error. So you see that there's some error and that the error is actually not that small. And it comes also with a standardized coefficient, which in this context is less important, gives you more like a unstandardized weight, with a t-score, because it's a t-distribution, resembling a normal distribution. And it's a small sample size, and a p-value, which is shown here as sig. That's typically SPSS, actually misnomer, I found. So we have here p-values that are 0.176, which is greater than 5%. We have 0.155, which is greater than 5%, and sleep problems, 0.000, which is also wrongly expressed. And I don't know why SPSS would do that, but it's basically smaller than 5%. So that means that all that's really significant in this model is basically sleep problems. So sleep problems basically override the stressful life events that we thought, based on our univariate model, would be significant predictors. And this is where the value of multiple regression basically is very apparent, because factoring in a new variable sometimes really changes your perception of the initial variable you have analyzed. And that's super important to keep in mind. But again, this inclusion is essentially, it's art. It's not easy. So it requires a lot of reading, it requires a lot of consideration, and it's not straightforward. Good. Yeah. Lastly, yeah. Okay, so that's a nice slide. Okay, we will do a multiple regression a little bit more on Wednesday. And you have seen already the videos. There was already talk about artificial intelligence and regression models and prediction. Literally everything in your surrounding uses in some shape or form multivariable regression. You have apps and websites, you have forecasting, anticipatory shipping and shopping. That means every app you have on your phone uses some form of logistic regression or some form of a multivariable regression model to predict what you will be clicking next. And it will do that to optimize its performance. You will have forecasting of various parameters, can be weather, can be stock market prediction, can be prediction of whatsoever. Anticipatory shipping. That's the only reason why it's actually possible to support a large population in a city like New York, for example. The only reason why they can actually do that is because they know and they have predictions of how many apples people in Midtown East are gonna be buying in the next 2 days. Because these are models, particularly the large chains. Obviously, the daily around the corner is not going to have the most sophisticated model. But basically, if you have a large supermarket, they know exactly what's coming in. So they build models predicting what will be bought tomorrow. Or some large online shopping websites, for example, that basically deliver within a day. anticipatory shopping, otherwise they would be out of a job. Shopping, same thing. You open your phone, you go on any website, the website is giving you already suggestions what you will be buying or what you would be interested in. Multiple regression. So, and this is really where the beauty and the applicability of these methods becomes very apparent. Good, that's all. Thanks so much. Have a nice evening. Yeah. Let me just stop the recording.